Hello, this video is section 2.4, measures of variation. How data is kind of scattered amongst itself. We've covered central tendency in the last section. The first most basic measure of variation, and the easiest to deal with, is called the range. The range is calculated as the maximum data entry minus the minimum data entry. So in a small data set like this, I don't think you necessarily would need to sort them. It would be more convenient if it was a larger data set, but even then you still shouldn't have to. But anyway, if they're sorted, it'd be the right one minus the left one, but this one's clearly not sorted, so you're just looking for the largest value of this data set, which is 24. The smallest value is 2, so we subtract. 24 minus 2 equals 22. That's really all there is to range, nothing to it. Now we have something called a deviation of a data value. Whether it's population mean or sample mean, it's essentially calculated the same way. If you take any particular data value in your set X and you subtract the mean, whether it's population or sample, that gets what's called a deviation. Sometimes those deviations are going to be positive if your X is bigger than the mean, negative if it's less than the mean, or the deviation would be 0 if your X value is exactly the mean. Now let's look at this. I'll get a population data set we're going to look at first here. So this is defined to be a population with these 5 numbers. And we're going to calculate mu, which the mu is our Greek letter for population mean. Sum of the X's divided by n, capital N, which is the sample size, population size, excuse me. So easy enough, 46 divided by 5 equals 9.2. Now suppose we take each deviation, and I'll show you real quick how to get these without worrying about, well, they're written out here too. Come over here. So each deviation, you take the number and you see we're subtracting 9.2 every time because that's the mean. So we got some negatives and positives. So let's say we want to see maybe how scattered the data is by just taking an average of the deviations. So if you take these 5 deviations and you add them up and divide by 5 equals 0. And that would imply no deviation. Average deviation 0. That doesn't tell you anything. And there's only one way that a data set would have no deviation is if every numerical value was the same number in your data set. So this is worthless for us. And it's, you can be derived using the formula. I'm not going to worry about showing you that. But I promise you it's going to be 0 every time if you just average the deviations, because the sum of the deviations will always add up to 0. Now, to get rid of the idea of having negative deviations, because really negative, we're looking more for distance away from the mean than we are worrying about whether it's negative or positive. If it's far away from the mean, we don't care whether it's below or above. So to take care of that, we square the deviations to get rid of all these negatives. So you take each of these numbers, square them, and you'll get these numbers right here. Add them up, you get 44.8. And that number 44.8 is called the sum of the squared deviations. All right. Now here's a formula called population variance. I don't anticipate you having to really use this formula other than just showing you this first example. We will use technology to calculate this, but it's always good to see where something's coming from. So this thing called population variance is measured with the lowercase sigma, and it's got a square there. Anytime you have a variance, it always has a square with a variable. That little 2 is kind of small to see, but it's there. So that numerator is the squared deviations divided by the population size. So from above, we calculated 44.8 as the sum of the squared deviations divided by 5, 8.96. And right here it's saying the population variance is just the average of the squared deviations for a data set to get rid of those negatives. Now we have something called standard deviation. Standard deviation is always going to be the square root of the variance. In any situation, we're going to have different things that produce variance, and the standard deviation of whatever that thing that produces a variance will always be the square root of that variance. And so it doesn't need to be completely recalculated. So it's just the square root of the variance. So you would take the square root of 8.96, 2.993, and here's what I was mentioning, what I said about being the square root of the variance. One reason standard deviation is generally more used than variance, because when you're squaring those deviations, you're kind of altering the numbers kind of a bit. You know, you're staggering the distances more. So the square root kind of brings it back down a level. So squaring them gets them all to be positive, but then the square root gets them back down to a more reasonable measure result. That's the only reason. But obviously they are related by the square root sign. And I'm not sure if I mentioned that in the notes anywhere about what I was just saying about the units of measure mainly. Like, for example, let's say it was measured like in dollars or whatever, and the variance would actually be squared dollars, which really makes no sense. So square rooting it back gets it back to a proper unit of measurement. And anyway, that's enough of that. Now we have sample variance. Now, one thing we've seen is population mean and sample mean are calculated the exact same way. Variances are not. And the difference is the numerator is still the sum of the squared deviations, but you're dividing by n minus 1 instead of n. Now, there's a whole bunch of theory and reasons of why it's n minus 1 divided by n. I think I've included something here at the end that you don't have to know this. You know, you can read that if you want to, but in summary, it's using n, because you're generally going to be using the sample variance to estimate the population variance, and n minus 1 dividing by n minus 1 gives you what's called the best unbiased estimator. That's a statistical term we don't have to worry about here. It is right down here, unbiased estimator, and there's a lot of math that comes up with this. And the idea is it makes so that way you're making the sample variance. If you divide by n minus 1, it makes it larger, because anytime the denominator, you reduce the denominator of a fraction, it makes the numerator larger. So you're kind of trying to overestimate it a little bit if you can to make it more reasonable. So there's a lot to that, but the good news is you don't really have to care about that. And the technology we'll be using will take that into consideration. So there's the difference. Now, taking that data we had, the last example, and using, it's the same squared deviation. So if you wanted to get the sample variance, the only difference is we would take that 44.8, and instead of dividing by 5, we would divide by 5 minus 1, which is 4, and we get 11.2. And then, of course, the standard deviation is always a square root of variance. So if S squared is your sample variance, S will be the sample standard deviation. It will be the square root of 11.2, which is 3.347. And there you go. Now, I'm going to show you this in real time when we do my MATLAB Stat Lab problem here in a little bit, but I'll kind of walk through this. So I'll show you. You'll get to see me do this. So here are the 5 numbers, and you're going to use the command stat calc 1var stats. It's the same command that you use to, you can get mean and median from that same command. Now, one thing about this command is you don't get the variances. You only get the standard deviation. So you see this SX right here, the 3.3466, that is your sample standard deviation. And there's your sigma x right below, that's your population standard deviation. And you can check back above in the notes, and that's what we got. But to get the variance, see, you have to square those numbers. In other words, to go from variance to standard deviation, you would take the square root. To go from standard deviation to variance, you would square. So for example, if you were told, okay, the standard deviation is 5, the variance would be 5 squared, which is 25. So here we had to type, I don't know if you necessarily had to use all those digits or not, that's maybe not I know sometimes my stat lab can be picky, but I went ahead and put them all in there, squared it, and got the 11.2 that we got earlier for the variance, and then typed in the population value, 2.99, blah, 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 squared it, and got the 8.96. So here's where I was just saying I put that in writing, and you have to square it to get the variance. Now with Excel, there are 4 individual commands that will give you each of those, and you don't have to do all that squaring business. And you'll see me do these, but here are the commands right here, and you'll see it for an example coming up. And there are the 5 numbers, and I've labeled them, and then there's this, it shows the command that's typed into the cell where the values are. Population variance in Excel is var.p. Makes sense? P for population. You can't see the labels, but that is column A, so it's A1 to A5. You could be in a different column and use whatever you have. Now, population standard deviation, I could do that one of 2 ways. I could take the square root of the answer above it, so I could square root it, but it has its own command. stdev.p, A1 to A5, gives you the 2.993 thing. Sample variance, var.s, okay, S for sample, that makes sense. A1 to A5, be 11.2, and just like the population, to get the standard deviation for the sample, I could just square root it, but I don't need to, because I can do that, or I can just use this command, stdev.s, A1 to A5. So I think that's real convenient. Now here's this thing that's from the data analysis tool, the descriptive statistics. It has all this other. Now this isn't overly helpful for this. This could be good if you had a problem where you want mean, median, mode, standard deviation. But this is all, these 2 command things I've highlighted. It only does sample standard deviation and sample variance. See how these 2 numbers in yellow and blue match these 2 numbers right here. It doesn't put out the population. So this really does you, if you only wanted sample, it would be fine, but it does you no good if you want the population. You would need to use these individual commands. So I'm not sure if this helps, unless it just, gives you some other numbers you might want to use at the same time, then it's handy. But like I said, if it was a multi-part problem where if it wanted mean, median, mode, and sample standard deviation, that would work. It does the range for you. Range would be highest minus lowest, like we saw, it'd be 13 minus 5, so it'd be 8. Okay. Anyway, but these 4 individual commands work really well. I would kind of give that as an edge over the calculator, because the calculator only gives you the standard deviations and not the variance. Okay. Now here's a new block of numbers: 8, 11, 14, 8, 11, 7, 14, 10, and 4. And they are entered in here using stat edit, and you can put them in stat edit. It brings you to the list menu. And that's these numbers entered there. Then you quit out of that and do the 1 var stats thing. And there's everything you get. But then let's say you only get the standard deviation, so you have to square these numbers. I didn't use all the decimals this time to get your variances. Sample variance is 12.0 basically rounded, and that one's 10.0 rounded. 12 and 10. All right. Let's see. That's weird. They came out whole number answers there. I don't know where I got that example from. Usually, there's nothing wrong with that, but usually you're expecting them to have decimal answers. It's rare for them to have whole number answers. But anyway, so here we are using the Excel command. There are the 6 values. var.p, A1 to A6, and we can look at the calculator result to kind of compare it. var.p gives you the 10, which is right here. stdev.p, A1 to A6, we have 6 numbers. There's your 3.16, that's what the calculator spit out right there in that bottom row. There's your sigma x. Your little lower sigma, that's your population standard deviation. Sample variance, bar.s, right there, 11.9999, which is 12. And standard deviation, STEDEV.s. And then here's the standard deviation in the calculator, right there. Alrighty. And here's another one. I didn't show the data input. Guess I could have. I'll move that around a little bit. Well, I guess I don't really need the space, do I? Oh, well, that's all right. Leave it as is. Got a little extra space. I'm not going to move a bunch of stuff there. Oh, this one, let me go back and look at the instructions. This one, it just wanted the standard to 2 standard deviations, which that comes right out of the calculator perfectly. I didn't want any variance. So you see I only used the 2 standard deviation commands in Excel. But there's the output in the calculator. I know I didn't show the entry, but if you look at the data in Excel and you see these 2 answers versus what's in the calculator, that's a pretty good likelihood. It's pretty much a guarantee that I did type these numbers correctly in the calculator. Hey, we're all human beings, you know, even though this is not that, you know, over that bad, you know, I can mistype a number anytime, you know, so even though you don't see the numbers, you can see there's a match. So that probably guarantees I got them in there correctly. So that's they're proper. So there you go. Okay. Okay, we'll save some live examples here in a little bit. Let's look at something called the empirical rule. Now we're getting into the idea and standard deviation being more used in variance. Now we will look at how the mean and standard deviation work together to provide information about a data set. They team up very nicely in many situations to tell you things. And the first thing we're going to look at is called the empirical rule. And the empirical rule only applies to what we call a symmetric but bell-shaped distribution. We've talked about, symmetric can be in different forms, but this is symmetric bell-shaped. It looks like this one on the left here, which we're going to be talking in Chapter 5 a lot. We're going to be all about that curve. That curve is graph's very important to statistics, but I'm not going to spoil your fun with it now. Other than I'll tell you it's called the normal curve. Anyway, now suppose that data kind of maps out to where it's shaped in this form, where the curve would form like shape or very close to it. It doesn't have to be perfect, but so for any distribution of data that maps out and graphs to look like that bell-shaped distribution, or also sometimes called mound-shaped, same thing, about 68% of the data lie within 1 standard deviation of the mean. Okay, so what is exactly is that telling us? That's telling us, and we'll look at examples, of course, but that's telling us if your data set has whatever the mean and standard deviation are, if you create an interval, and it doesn't really matter whether it's population here or sample here, I wrote them both, either way. If you take the mean minus the standard deviation, and you create an interval, well, that number's on the low end, and then you add the standard deviation to create an interval on the number on the high end of the interval, you get a range of values. If you went through your data set and you counted how many values were in that interval and divided by the total number of values, you're expecting that to be very close to 68%. Now this will generally hold true, they need to be kind of larger data sizes. It doesn't really do you much good if it's only like 10 numbers or something like that, but it should hold very close to that if the graph is bell-shaped. Now the next one, we're going to create a wider interval, which of course will include more numbers, and that will change the percent. Here we take the mean and subtract 2 times the standard deviation to get the low end. You take the mean and add 2 standard deviations to get the high end. You create an interval, that's a bigger interval with more numbers, and you do the same thing, you count them up, how many that fit in there, divide by the total. You're expecting about 95% of your data to be in that interval. And the last one, 1, 2, 3, you take the mean minus 3 times the standard deviation, the mean plus 3 times the standard deviation, you create an interval, and you're expecting about 99.7% of the data to be within 3 standard deviations of the mean. That's also known as virtually all. You know, sometimes books will say virtually all. And here comes that word we've used before, outlier. We've been, told you to keep popping up here and there. So you can safely identify any value that's not in that third interval as an outlier in your data set. Okay, let's look at this. Let's look at an example with numbers here. Help clarify this idea a little bit. I think once you see, look at this. So here are some numbers. You've got a mean 60, standard deviation 8, bell-shaped distribution. If you take 60 minus 1 times 8, you get 52. 60 plus 1 times 8, you get 68. About 68% of the data should lie between 52 and 68. Okay, come down here. If you take 2 here, the second part of the empirical rule, 60 minus 2 times 8 will be 44. 60 plus 2 times 8 will be 76. So we're expecting about 95% of the data should lie between 44 and 76. Next one, you take 60 minus 3 times 8, 60 plus 3 times 8. So 60 minus 3 times 8 is 36. 60 plus 3 times 8 is 84. And we would expect about 99.7% of the data should lie between 36 and 84. Now here is an example. You are not going to have to do this, so I want to walk through this real quick. I mean, anything in the homework, it'll be just small data sets. So you don't have to worry, but this was easy for me to do in Excel and kind of without, I'm not going to, I could do a new one, but that's all right. That would only be important if you were going to have to do it. So what I did is I went to this in that data analysis, that tool pack thing that needs to be added to be able to do this. Also, that's the one I was telling you about before for descriptive statistics. If you ever want to use that, you have to add in that tool, that tool pack. Random number generator. So I took 200 numbers. Zoom in a little bit. The distribution is normal distribution. Like I was saying earlier, the curve is also called the normal curve distribution. Put in mean 60, put in 8 standard deviation. You have to put in just some random 4-digit number. No, that's not my PIN code or anything, so just made that number up, and then I put an output range. Now, when it comes out of Excel, it comes, it would spit the 200 values down the left column. So what I did, I sorted them and then put them in blocks of 20 going across. Just, I didn't want 200 numbers going straight down a page here for this because it's not that important. So we now there's 200 values, and then we have, these are the same intervals that we calculated right up here. These 3 right here. So what I would do is for the first one, I go through and I want to find everything between 52 and 68. So that literally means, no rounding. You want to find the first number that just barely squeaks past 52. 52, excuse me. So I don't want 51.98, doesn't count. There's the first number that's at least 52. Then on the high end, I want to stop just before it gets to 68. I can't go over 68. And if you count all the numbers between here, actually, it's not that hard to count them. And I'm not going to, but they're being in blocks of 20. Kind of makes it easier to count them. But anyway, long story short, once again, this is not that critical for you to have to do. There were 136 of them, which is 68%. So what we're trying to do is with this sample, we're trying to see with this particular sample, how close is it to the empirical rule. So over to the right, I have the empirical rule values. This one matched exactly. 136 over 200 is 68. And that empirical rule says 68. So the next interval is between 44 and 76. Okay, I'll go ahead and speed this up a little bit now. So you want the first number a little bit bigger than 44, and you under 76. Actually, it's easier to see that there's 5 numbers outside that region, so 200 minus 5 is 195. So this particular data set had 195 values divided by 200, which is 97.5. Empirical rule says 95, but 97.5 is not bad. You know, it's in the ballpark. You know, the larger the sample, the generally more accurate it'll probably be. If I would have done 2,000 numbers, you know, it'd probably been a lot closer. And the last one, 36 and 84, they are all between 36 and 84. Sometimes if I'm teaching a face-to-face class, I'll do an example with maybe 1,000 numbers just to show them. And you'll catch one that maybe falls outside there. You know, you might get like 99.8 or 99.9, but this one, no outliers, they're all in there. But yeah, there's nothing wrong with getting 100% when you're expecting 99.7%. That's pretty close. But I hope you don't feel cheated that I didn't do a live example of 1,000 numbers there or whatever, but that's okay. Okay, so okay, here's kind of a question. These questions could ask on a test or something. Mean value sample of farms is 2,400. Standard deviation is 450. Between what two values do about 95% of the data lie? Assume the data is bell-shaped. That means empirical rule. So, like I said, you just go back and you refer to these. Just have these conveniently handy in front of you. See, there they are. 68% is 1. I'm not expecting you to already memorize that just on what I've said, but to be able to refer to it. 95 is 2. 99.7 is 3. So 95, which is our problem, is 2 standard deviations. So that's exactly where I'm getting that from. So there's where the 2 is coming from, the 95%. So you just do these calculations. Easy. You would expect 95% of them to be between 1,500 and 3,300. Next one is just the opposite, where it gives us the interval and we have to figure out the percentage. So either one of these kind of formats of a question could be asked on a test. It's giving you the mean and standard deviation. What percent of the data would you expect to be between 44 and 116? So we're trying to figure out whether it's 1, 2, or 3 standard deviations, because that way we'll be able to get the percent based on that. There's 2 ways you can do this. I just wrote a little equation where K represents a number of standard deviations. Whether you solve minus to get the lower or plus to get the upper, or you could solve it algebraically and you'll get 3. But here's another way to do it. And you can do either subtract or add. We know it's going to be 1, 2, or 3 for the empirical rule. So I chose to subtract. I could have chosen to add. I went 80 minus 12 to see how many times did I have to do that to get to that lower number 44. I did it once? No. Twice? No. Third time? Got it. So it took 3 subtractions of 12 to get to 44. So I guarantee if you did 80 plus 12, it would take you 3 times to do that to get to 116. So subtract or add, it's going to be 1, 2, or 3. And then once you know it's 3, the definition in the rule, a few pages back there, gives us 99.7. Here's another similar example. I wrote the equation. I guess I didn't put the calculator screen in this one, but okay, it's 60 mean, standard deviation 13, 47, and 73. Okay, I'll go plus this time. I'll be shooting for the high number here. So I'm going to go, how many times do I have to add? If I go 60 plus 13, well, looky there. We got it on the first try, didn't we? 60 plus 13 is 73. It only took once, So the K equals 1, which by definition of the empirical rule means that the answer is 68%. Okay, play around with that a little bit. I think you'll get the hang of it pretty quickly. Now here's a theorem for data that's not bell-shaped, Chebyshev's. It's not a very accurate result. It's almost like a better than nothing. The empirical rule is good, but you can't use the empirical rule if the data is not bell-shaped. So data that anything that's not bell-shaped, it could just say not bell-shaped, or it could say unknown shape, skewed left, skewed right, not bell-shaped. Now, one thing that's important about the wording of this is the answer must say at least. See, for the empirical rule, we're calculating more of a precise result, so it can say about that percentage, meaning it's just that percentage. Here, they're just treating it as an interval. Here's the actual formula based on your K, so you can calculate this for, K has to be greater than 1, though. We can't use 1 in this theorem. But anything greater than 1 can be used. So it must say at least. That's why I highlighted that in red so you can see it. Now here it is for 2 and 3. I did the calculation for 4, but I can tell you that anything in the homework or on an exam, I'm either going to use 2 or 3. I'm not going to use anything other than that. But now you don't have to make this calculation. Now you know when it's 2 standard deviations, it's 75%. When it's 3, it's 88.9. But just to show you, there's how you get it. So if it's 2, for Chebyshev, at least 75% of the data lie within 2 standard deviations of the mean. And then at least 88.9% of the data lie within 3 standard deviations of the mean. So you have to be careful when you're doing a problem, whether it's going to be empirical rule or Chebyshev, because I could easily have answer choices on a test that have at least 75%, which is correct for 2 on Chebyshev, and then I could have about 95%, which is correct for 2 on empirical rule. They could both be in the same set of answers, so just pay careful attention to whether it's a Chebyshev problem or an empirical rule problem. If you do that, you should be A-OK. Okay, mean time 57.07, standard deviation 1.05. The shape of this data is unknown. Find the interval that contains, I'll go ahead and just change this while we're at it, at least 75% of the data. You come up here. You don't have to make any calculation here. You just have to look up here, and then your K is 2. When it's for Chebyshev, when it's at least 75. That's how we know it's 2. We come down here. We take the mean minus 2 times the standard deviation. We get 54.97 at the low end. 57.07 plus 2 times the standard deviation to get 59.17. So we're saying at least 75% of the data should lie between 54.97 and 59.17. Now let's do the same thing where we're given like we did before, where you're given the interval and you've got to figure out the percentage. Skewed right. Well, skewed right. That's enough to tell us it's not bell-shaped. That implies Chebyshev's rule, not bell-shaped. Got a mean, got a standard deviation, that's going to be given to you. What percent of the data would be between 50.4 and 69.6? So I'm doing the same thing that I did with the empirical rule for these problems. Well, I wrote an equation out, if you want to do it that way, but you don't have to, just do this in the calculator. I chose to add this time. It doesn't matter whether you add or subtract. I chose 60, and I had to figure out, okay, how many times do I have to add 3.2 to get to 69.6? And you could see it took me 3 times of adding 3.2 to get to 69.6. 3 times. So how about that? And there it is. So 3, and then you go back up here for the definition for 3. Like I said, I'm only going to be working with 2 and 3 on this. 3, at least 88.9% is the rule for Chebyshev when K equals 3. All right. Let's look at something called the standard score, the z-score. We'll also be using that later on too when we come back and revisit the normal distribution. Basically, the z-score is the number of standard deviations a given value falls from the mean. The z-score, it's an easy computation, also known as standardized value. So whether it's population or sample, it doesn't really matter. When we're dealing with this later, it's mostly going to be population, but you take whatever your value is, you subtract your mean and divide it by the standard deviation. So without even doing the calculation, I'll just sort of say an easy example verbally. Let's say if your mean was 40 and and standard deviation was 8 and your value was 48. So if you took 48, which is exactly 8 above 40, right? So it's one standard deviation above 40, because 40 plus 8 would be 48. But if you do the calculation, 48 minus 40 is 8, divided by 8 is 1. So you get a z-score of 1, meaning your value was exactly 1 standard deviation above the mean. But these are going to have decimal answers. We're not, it could be 1.3 standard deviations above the mean. Negative 2.4 could be 2, it means 2.4 standard deviations below the mean. So if your z is negative, that will indicate your value is less than the mean. If z equals 0, the value is the mean. Z greater than 0, your value is greater than the mean. Now, here we have a data set with mean 52, standard deviation 8. Just find the z-scores for 3 particular data values from that set. So the first one be 64 minus 52 divided by 8 is 1.5. 38 minus 52 divided by 8 would be negative 1.75. And then 52 minus 52 divided by 8 equals 0. And there you go, easy calculation. Now let's use the z-score to kind of compare better relative position. It's kind of like a ranking kind of thing or something or another. And for this kind of example and anything I would ask you on a test, we're looking for the larger z-score. But there's situations in real life where a negative z-score would be better, and that would kind of be something if it involves you having to sort of like pay for something, whether it's like, let's say you bought a new car or something and you found out that your z-score, what you paid was -1, and someone else was negative, or someone else was even, z-score was 0. You actually did better at -1 because you paid lower. But in this one where you're trying to achieve something being like a test score or something higher like that, positive z-score is better, and that's anything I ask on a test would sort of be similar to this, where we're going for the positive z-score. But I just want to mention, in reality, sometimes negative z-score can be good. Okay, we got the same student here, Arlene. She is taking a stats class. The mean was 80 and standard deviation was 10, and we had this accounting exam which looked like it was really, really difficult, with a mean 65 and standard deviation 12. She makes a 90 on the stats exam and an 80 on the accounting exam. Which score has the better relative position to the rest of the class? So obviously you look at this and you would say, well, 90 is better than 80, but we're looking at it, in other words, is the 90 on the stats exam put her at a higher ranking than the 80 does on the accounting exam? That's what we're looking at. Fortunately, we don't have to really overthink this. All we have to do is calculate the z-score. That's all you have to do. And this kind of question, when it's on a test, and it could be a tie, they could be exactly the same, but the answer choices are going to be, whatever, first one's better, second one's better, or they're both exactly the same. That can be an answer. So on the stats exam, 90 minus 80 divided by 10, 1.0. So Arlene was exactly 1 standard deviation above the mean. Accounting, 80 was the score, minus 65 the mean, divided by 12, 1.25 z-score. So actually the z-score was higher on the accounting exam. So that's what we call the better relative position from a ranking standpoint, was actually on the accounting exam, even though it was, she made a higher score on the stats exam. So there we go. There we have it. So that's all you have to do in this kind of question on test, is just compare the two z-scores. Not too bad. And this is the last thing in this section. The last page is just, I'm not going to read. You can read that if you want to, but I've already talked a little bit about that earlier. Why do we divide by n minus 1? Fortunately, the technology you use, whether it's the TI calculator or the Excel, takes care of that for you. So the coefficient of variation, and this is kind of interesting, this kind of compares data between two different groups where they have different means and they have different standard deviations. You can't really just compare standard deviations itself. You know, the standard deviation does measure how scattered it is, but let's say we have I'll write down the same mean as an example here, but let's say we have a mean of, and I don't know, 50, and our standard deviation is 6. I'm not even going to write that out. And then same thing here, the mean is 50. And standard deviation here is 12. Okay, if they're both the same mean, 50 and 50, 6 and 12, that standard deviation measures how spread out the data is. That tells you for sure that the data is more spread out for the data set with a standard deviation of 12. But however, if they're different means and different standard deviations, you can't really make that. You can't just compare the standard deviations. That's what I'm saying. What you can do with the mean is the same. So this is a pretty easy calculation. Doesn't matter whether it's sample or population. You just work with whatever you have. You take the standard deviation, you divide it by the mean, and this can be over 100%, by the way, and multiply it by 100, and that's how you get it. And the answer is in percentage form. So we have a data set with mean 50 and a standard deviation of 20, and another data set with a mean 200 and a standard deviation of 40. So what I was saying, you can't automatically look at this and go, oh, 40 standard deviation is bigger than 20, that means it's more scattered. Well, see, we can't do that because the means aren't the same. If the means are the same, we can absolutely say that. So easy calculation from the first data set, you take 20 divided by 50, multiply it by 100, you get 40%. For the second one, you take 40 divided by its mean of 200, and you get 20%. So actually the first data set, even though it has a smaller standard deviation, it would be considered more variable than the other one. So how about that? Before we conclude this section and head to the homework, last thing I want to show you is just to kind of give you a feel for the values close together versus spread out a little bit more. Now this is, I took a data set that we used earlier, these 5 numbers on the left, and then I made up 5 new numbers, but I wanted them to have the exact same mean. So notice that these numbers there, I intentionally made them closer together. You know, not very much spread out business here, but these numbers that we had originally earlier are more spread out, and notice they produce the exact same mean. But like I said, the idea is that the means are the same. The larger standard deviation will guarantee the numbers are more spread out, and so that kind of pans out from the calculation. So there, that's all this is. Really isn't anything that critical here for you to see, but you can see this one has a 3.34 whatever, and that one only has a 0.837 standard deviation, and it should be bigger standard deviation here because the numbers are more spread out. So now it's time for some MyStatLab homework. I'm going to start with question 6 here from the 2.4 homework assignment. I'm going to do this because I've been promising you to show the calculator. So I'm going to show calculator and I'm going to show Excel. And you are free to do whatever makes you happy. That produces the correct answer. Yeah, let's clarify that. So even though these are already in Excel, I'll come back to the Excel command, but I'm going to put the stuff in the calculator. Let's see if I can move this over where I can see those numbers. Clear. So you go Stat, Edit, and then to get rid of a list, if you arrow up and hit Clear, then you arrow down again, and then they all go away. It's weird that they don't go away when you hit Clear the first time, but you got to move the arrow down, and there they go. So let's put these in there. 2. Order does not matter. It will. 3, 14, 7, 12, 9, 4, and 10. So we go second and then quit to get out of this. Then we go Stat, Calc, 1 var stats, L1. That's why I always like to keep the data in L1. And let's see. I think what I'll do is I'll snip this out. Oh, that was a problem we did earlier. And put it on the, because we're going to compare it with the Excel. So I can type these answers in right now, but I'm going to go ahead and do the Excel commands at the same time, just to make sure that everything agrees, you know, before we go. Looks like it's going to want range, mean, variance, standard deviation. Oh, but it's population, so it's population. So we're looking at defining. It's important that we see if it's defined as be a population or a sample. Now I need to bring the calculator back here for a minute. No, I think I got everything I need there. Yeah, I got the range. Yeah, the calculator doesn't show the range, but I'll tell you what I'll do. I'll snip this out. You can arrow down to, and we'll be dealing with this bottom part very soon. The next section, I believe, that Q1, Q3, that's coming up. So let's put this here, and I'll try. Wonder why that didn't work. Edit. Okay, I don't know what happened. Let me shrink this down a little bit. We can always zoom back in later if we need to. So we have some information there, and since it's population, I don't want to use the descriptive statistics. I want to do, you know, the range probably has its own command in Excel, but the reason why I put this other screen and the calculator is you can get the range by going max minus min. So 15 minus 2 is going to be 13 for the range. But I never really have tried. I think range probably is a command in here. Maybe not. Maybe it isn't. But that's okay. You can sort them if you want to. You know, you didn't have to sort them, but if you did sort them, yeah, for the other calculations, if you do that, then you know it's going to be the last number minus the first number. 15 minus 2 is 13. So I'll go ahead and get that check mark real quick. 13. All right. Population mean. Now keep in mind, once again, the calculator, even though it shows X bar, it only shows, it's showing the mean, because the mean, it's the same calculation, so whether that's X bar or mu, it's going to be 8.2. But I want to go ahead and do the command here, the average command. A1 to A10. And I can put the formula text right back here so you can see that. That's in cell C1. Oh, I always like for these to be centered, just, I don't know. Maybe I'm a bit OCD or something. So there's the mean, 8.2, and the calculator is 8.2. It's all big one happy 8.2. Oh, come here. Fantastic. Population variance. That is going to be, I'll do it here. var.p, A1 to A10. Copy that down, you can see it. Now the calculator does not give you the variance, only gives you standard deviation, so I'll bring up the calculator. I can do it in Excel also either way, but I'll just put it here. I don't know, I'll type in a bunch, however, I don't think we need a bunch of them, but I'll probably just do it anyway. 1, 3, 3, 1, 2, 8. Yeah, probably doesn't need all these, but I'll just put them in there anyway and hit the X squared key over here on the left. So that's 17, that should be, oh, typo, I see it. I know I saw the answers didn't match. Okay, somehow I put a 1 here between the, let's delete that. 4.33, 128, 1566, let's try that. There we go. So you see that's 18.76. And the Excel gives you 18.76. Why is that not right? Populate, let's see. I got tricked by the rounding. It tricked me. If it can fool me, it can fool anybody. I typed in 18.76, which is mathematically correct, but see the first one said nearest tenth, but our answer was 8.2, so I just entered it. I didn't even think about it. Yeah, boy, you got to really read how many decimal places it wants. Wow, it got me. So we didn't do anything wrong. It's just the way we entered the answer. But on a test, that's not going to be a problem because whether the answers all be rounded to 1 or all be rounded to 2, it'll all be, you're just picking the right answer. You're not having to worry about typing it in. So population, it wants a tenth again, so I won't make that mistake again. Now we already have the calculator already has that number, but I'll go ahead and enter the command here, pretend like if you were only, so stdev.p, that is your, let's bring this down so you can see it, the command, if you look at it later, there we go, 4.333, and there we go, 4.333, blah, 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 nearest tenth, 4.3. You won't fool me this time, you sneaky MyStatLab. Sneaky. Got it. Okay, so there we go. So obviously it's trying to tell you whether it's a sample or a population. And of course the question helped by saying that too. Let me see what all's in this question. I may just skip it. It's good for you to have two of them to do. Okay, I won't do this one, but this one is a sample instead of population. So the Excel commands, you just use the samp bar.s and stdev.s. I have complete confidence in your ability to do that. The utmost faith. I got an empirical rule. I could do this one real quick. There's a Chevy Chev. Coefficient of variation. Yeah. Okay, this one I'll just say verbally real quick. Obviously, it'll be different when you make it a different percentage, but yeah, okay, real easy. So it tells you, let's see, between 60 and 78. So if you take your mean is 63, your 69, your standard deviation is 3, you would have to add 3 times to get to 78, and 3 is 99.7 in the empirical rule. I'll skip over these. 2, that means for Chevy Chevs at least 75%, so you would just take 84 minus 2 times 5. 84 plus 2 times 5 is 94. I guess I did basically do them there or whatever, but I want to do this coefficient of variation. Now, the thing here is unlike the example. Let me do this. I can do a fresh one. It's giving us data instead of the actual standard deviation and mean. All right, to save time a little bit here, I'm only going to do this one in Excel. I'm not going to retype these in the calculator. Obviously, I wanted to type at least one in the calculator so you could see it. And if that's your preferred method, that's wonderful. This will keep the video down a little bit time-wise. And it did say sample. So we want the sample mean. Well, that won't matter, but sample standard deviation is going to matter. Now, be careful because of the labels. It starts in A2, not A1, and goes to A13. And that's DE2. And I want sample standard deviation here. So it's going to be equal stdev.s A2 to A13. Now there's no real program command for the coefficient of variation, but it's standard deviation, which is D3 divided by D2. Now you could format this as percentage if you want to, but I would go ahead and just put times 100, and that way it's already in percent. But you could format the cell to be. All right, so there it is. Now let's don't get tricked by the rounding. Nearest tenth, I believe it was 6.12, so 6.1. All right, weights. And we should, if I do this, everything should hopefully to work properly here. Let me copy these two commands over here. Well, if I copy this over here, since I don't have the cells locked in, yes, see, because the cells weren't locked with dollar signs, that means it was doing it. You see the you see the formula, it automatically moves it over to column B. So that's a neat little trick there. So when you do this, yes, I highly recommend Excel for this one over the calculator. Yeah, because that way you don't have to even retype. It's there. You copy it over. Here it is, and there's your coefficient of variation right there at the bottom. 1 decimal place means it'll be 9.8. Excellent. Weight is more variable than height. Larger coefficient of variation. It loves us. Fantastic. Oh, and that was the last question? Okay. Perfect. We'll stop there. And that will conclude this video on the measures of variation.